Bismillahirrahmanirrahim. I'm student Lujain Al-Qaisi. Today we are going to discuss our project that talk about brain-computer interface. We will start with a simple explanations of the brain and the functions of it. As a quick, this technology is a way of direct communication between the human brain and the computer without need to use other body organs such as the peripheral muscles. As the brain-computer interface allow a person to issue commands to any electronic device using only brain activity, which provide artificial intelligence with a great opportunity to be an ideal assistant in the processing of signal from brain before it reach the prosthetics. It using electrode to detect electrical signals in the brain, which are sent to computer. The computer then translated this electrical signal into data which is used to control computer or device linked to computer. Normally, connections are made between the brain and the muscles via motor neurons. This motor neurons in the brain relay a signal to the muscles to move. A motor neurons are damaged and those connections break. This results in muscles weakness and eventually disability. Brain-computer interface is the eventuality in that it makes up for the lost connections. Technically, brain-computer interface use an EEG to record the electrical activity of the brain. Those signals are then directly sent to the computer where the signal can be broken into pattern and interpreted. That happened in the three main steps. The first one is calculating a brain signal, then interpreting them, finally outputting command to connected machines according to the brain signal received. Now for brain. The brain consists of four loops. The partial loop, which is involved in the receptions and the processing of the sensory information from the body, and the frontal loop involved with discussions making a problem solving and planning. Optical loop involved with visions, or temporal loop involved with memory, emotions, hearing, and language. This will help us to know from where we can detect the signal. The most important part of to be useful in each or in this technique, the frontal lobe, we can detect the signal to control movement or contractions, thinking, or behavior. From temporal lobe, we can detect a signal to hearing or to memory or the smell. From optical lobe, we can detect signals to visions. And from brainstem, we can detect the signal for heart rate. The brain-computer interface started in 1970. This technique is a computer-based system that acquired brain signal, analyzes them, and translated them into commands that are related to an output device to carry out desired actions. This technique don't use the brain normal output pathway of peripheral nerves and muscles. This definitions strictly limit the term of brain-computer to systems that measure and uses signal procedures by the central nervous system. Thus, for example, a voice activity or muscles activity communication system is not a brain-computer interface. Furthermore, an EEG machines alone is not a brain-computer interface because it only records brain signal but doesn't generate an output that acts on the user environment. It's a misconception that a brain-computer interface are mind-reading device. Brain-computer interface don't read mind in the sense of extracting information from unsuspecting or unwilling user, but enable users to act on the world by using a brain signal rather than muscles. The users and the brain-computer interface working together. The user often, after a period of trying, generated brain signals that encode intentions, and the brain computer also, after trying, decoded these signals and translated them into command to an output device that accomplishes the user intentions. brain-computer system consists of 4 sequential components. The first is a signal acquisitions, feature extractions, وفeature translations, وdevice output. First component we can or استنى شوي وقف please. The first component is the process of measurement of the analog signal from the brain using different practical sensors. The second one is the process of extracting a unique feature form of recovered signals. The third one is extracted and classified. It's passed through the feature translations algorithm. A device output, or the least one, is a translations unit to provide to the specific output device. For brain-computer type, interface type, we have 3 types: the invasive, non-invasive, and semi-invasive. In invasive technique, special devices have to be used to capture data. These devices are inserted directly into the human brain by critical surgery. In semi-invasive, devices are inserted into the skull on the top of the human brain. In general, non-invasive are considered the safest and low-cost type of device. However, these devices can only capture weaker human brain signals due to the obstructions of the skull. The detections of the brain signals is achieved through electrode placed on the skull. There are several ways to develop a non-invasive brain-computer interface, such as EEG, MEG, MRT. An EEG-based brain-computer interface is the most preferred type of the brain-computer interface for students. That's what we say before. EEG signals are processed and decoded in control signal, which a computer or reported device receive readily. In this slide, we show a picture of this type. The first picture or above pictures is a non-invasive type. Name is the NeuroXi, like NeuroXi. The NeuroXi is used for EEG with one dry electrode, measure and attentions, meditations, and eye blanks. It's Bluetooth communications. For emotive was originally marketing for a video games where players control a various aspects within a game environment. The picture under it shows how electrode placed on the skull to measure electrical activity. For the last one is the invasive type. Show the intercontractile microelectrode array and its placement in the patient with disability. It consists of 100 microelectrode array on top of US penny. The microelectrode array is a scanning electronic micrograph. The square in the percentile gray shows the approximately locations of the array. The patient sitting in the wheelchair and working with and techniquing on a brain-computer interface task. The gray arrow point to a percutaneous deep pistol that consists of amplifier and other signals acquisitions hardware. Now we will talk about brain-computer applications within Jabber.
Now I will talk about brain-computer applications. There are a lot of applications used brain-computer interface, such as in cursor control, in neuroproteins and limb rehabilitation, in somatosensory and auditory sensation, and etc. Now I will talk about a specific application. I will talk about brain-computer interfaces used in neural prosthetic. It includes 3 processes. The first one is recording signal from neuron populations. The second one is decoding the signal using mathematical modeling algorithms. The last one is translating the intended action into physical limb movement. After the somatosensory feedback will improve by increased neural control by the patient and to avoid a more natural sensation for a prosthetic. This process involves recording data from first sensation location in the prosthetic and encoding this signal to be sent to the brain in the form of electric simulation, as we see in the figure. Moving objects with your mind, in the other words, brain signals are translated into commands using computer software. Those commands perform specific actions depend on the setup that we put on the computer. Such as switch TV. Through assistive living technology, one can control devices through special equipment, and one's thoughts in the example shown below. A television set is switched on by a person simply looking at a flashing LED light. The person's brain signals synchronized with the LED. Brain activity is then read by a specialized headset which connect to the computer. The computer program interprets the signal and sends the appropriate commands to switch on the TV. This phenomenon is called SSVEB. Now, I will talk about challenges and the proposed solutions to the brain-computer interface. Establishing the communication interface using brain signals has faced a lot of challenges. They can be categorized as technical and as usability. Usability challenges, they expressed the limitation facing the user acceptance of brain-computer interface technology utilized, such as training process. Training the user is a time-consuming activity, either in guiding the user through the process or in the number of recorded sessions. The second one is information transfer rate. It is widely used evaluation metric for command brain-computer interface systems. It depends on the number of choices, the accuracy of target detection. The last one is technical challenges. There are issues related to the recorded electrophysiological properties of the brain signal, which include nonlinearity, non-stationarity, and noise. We can solve all problems by adding noise removal, by improving a signal-to-noise ratio of EEG. The second one is separately of multiple classes. Machine learning techniques are employed to translate user intent into valid choices. In the conclusion, I will talk about that the brain-computer system based on AI is a rapidly advancing field in integration of medicine, neuroscience, and engineering. Although most studies that have evaluated AI applications in brain-computer interfaces to date have not been vigorously validated for reproducibility and generalizability. The goal of this device is to improve the level of function and the quality of life for people with paralysis. Thank you for listening.
مية مية.